everybody. We have learned about source coding and channel coding in the previous lectures. Today we will learn about pulse shaping. So we have actually the information at our end and we want this information to be converted into raw bits, and for that we have a source coder. The job of the source coder is to convert this information into raw bits with minimum or zero redundancy. Now these raw bits should be converted into the electrical waveform. For that, the line coding schemes are there, in which the job of the line coder is to associate electrical representation or efficient electrical waveform with the raw bits. We already know about several line coding schemes like unipolar, bipolar, Manchester, etc. So suppose we, after converting or using this line coding scheme, now we are going to transmit this information in a form of electrical representation. So suppose we are transmitting our signals by using rectangular pulses, and these rectangular pulses have some bit duration associated with them, and that is suppose TB. So when we transmit this information through a channel, we know that practically we do not have infinite channel bandwidth to transmit the signals. Wide channels behave like a low pass filter, and in case of wireless channel, bandwidth is a biggest constraint. So we cannot have an infinite bandwidth to transmit our information. So whenever this rectangular pulse is transmitted through this channel, then certainly we cannot have the infinite bandwidth, so some part of the signal should not be transmitted. Now we need to remember a very important rule which is used so many times in digital processing or digital communication or signal processing, and it is that if a signal is time limited, then it cannot be band limited, and vice versa. So if you have any signal, it means if you have transmitted the information using a rectangular pulse, then certainly in frequency domain or Fourier transform of this rectangular pulse, which is a time limited signal, certainly in frequency domain it should spread in from -infinity to +infinity. So if we have transmitted rectangular pulse in time domain, then its representation in frequency domain cannot be band limited. So Fourier transform of rectangular pulse, we already know that is sync pulse in frequency domain. So we can easily find out that sync pulse starts from -infinity to +infinity. So practically we do not have infinite channel bandwidth to transmit these signals. So certainly we have to say that bandwidth of the rectangular pulse is infinite. So certainly whole of the signal cannot be transmitted. So when this rectangular pulse is transmitted through this wired or wireless channel, due to band limited nature of the channel, high frequency part of the signal will be lost and only low frequency part of the signal will be transmitted. So it means some of the side lobes of high frequencies are not transmitted. So we know that high frequency part of the signal corresponds to fast changes in the signal in time domain. And since we have transmitted a rectangular pulse, fast changes correspond to falling edges of the pulse. Thus fall time of the pulse increases and the signal becomes a little smoother at the edges. So we can see that if suppose a rectangular pulse is transmitted, then certainly we require a bandwidth of RB in frequency domain. From the pulse it is very much clear that it is having a maximum value at the main lobe, that is 1 at t is equal to 0, f is equal to 0, and it is having 0 crossing at RB, twice RB, and so on. So we can see here that the transmitted pulse PT is rectangular pulse, but on the receiver side, received pulse is slightly spread in time domain due to band limited nature of the channel. So you can see that the transmitted pulse is a rectangular pulse, but in after transmission through the channel, on the receiver side, you can see that it is slightly spread in time domain. So it is not confined within the bit duration TB, slightly it is required more bit duration to collect the signal. The shape of the received signal even become more complex due to introduction of the noise and distortion in the channel. So we cannot predict the shape and size of the signal of the rectangular pulse whenever you are receiving. It means several pulses may have a different complex structure or complex shape. So normally the decision instant is at the center of the bit duration. Now because of the spreading of the signal beyond this bit duration, at the decision instant, we have only not only desired signal but other intended signal spilled over. Due to interference of the neighboring pulses at the decision instant, the detection of original signal becomes difficult and increases probability of error. So this phenomena is termed as inter-symbol interference. So you can see that at the decision interval, if other signals are interfering, then decision becomes difficult. So here we can say that when a rectangular pulse, which is time limited but not band limited, is transmitted through the band limited channel, then at the receiver, due to band limitation of the channel, signal at the receiver becomes band limited and thus not time limited, and hence inter-symbol interference occurs. To avoid this ISI, we need to have a pulse which should be band limited, because channel is band limited, and if the bandwidth of the signal we are going to transmit or bandwidth of the pulse we are going to transmit is less than the bandwidth of the channel, then there will not be any cutoff of the information. Thus we require to have additional pulse shaping block. So additionally, we know that if we have transmitted pulse PT and its Fourier transform in frequency domain is PF, then power spectral density of the signal will be given by SF is equal to PF square. Now this PF is dependent on the type of the pulse and the shape of the pulse. So we can say that the PSD of the transmitted signal can be controlled by two methods. Line coding, in which we are choosing the type of the pulse, and second one is pulse shaping, where we are choosing the particular shape of the pulse so that we can have the efficient control on the power spectral density. So requirement of pulse shaping is there that pulse should be band limited, and in general the bandwidth of the pulse should be less than the bandwidth of the channel. It means pulse spreads from -infinity to +infinity in time domain. It means it is not time limited. Second, interference of the previous and past pulses at decision instant should be 0, so that it should not be able to interfere with other pulses at their decision instant. So Nyquist suggested 3 criteria to reduce inter-symbol interference. First one was Nyquist criteria for 0 ISI, and second one was raised cosine spectrum. Third criteria is not significant here, so we will not discuss. Nyquist suggested that we can detect the signal if it is non-zero at a decision instant, even if inter-symbol interference is present. So Nyquist proposed a pulse such that it is non-zero at the center of the bit duration and it is 0 at all other decision instants or decision points. So Nyquist proposed a spot pulse shape such that Pt is equal to 1 at t is equal to 0 and it is 0 at all other decision instants, like at t is equal to plus minus n tb, where n is an integer number and tb is the bit duration. So sync function satisfies the properties of the signal proposed by the Nyquist. So equation of the pulse in time domain will be sinc of twice pi t upon twice tb, where tb is a bit duration, is equal to sinc of pi t upon tb, which is 1 at t is equal to 0 and which is 0 at all other instants of ntb. Maximum value of the pulse you can find at t is equal to 0 and its value is 0 at all other integral multiples of the pulse duration. Fourier transform of the sinc pulse is a rectangular pulse in frequency domain. So you can see that this is a band limited signal. So equation of the pulse in frequency domain becomes Pf is equal to 1 upon Rb pi f upon Rb, where Rb is the bit rate. In case you remember the previous case of the rectangular pulse transmission, the bandwidth requirement to transmit a bit was Rb. But in case of sinc pulse transmission, bandwidth requirement of the is half of the previous case of the rectangular pulse, and it is only Rb by 2. Suppose you have a binary sequence 10111, and here it is presented in the diagram how the bits are transmitted using sinc pulse. You are going to transmit sinc pulse for 1 and negative sinc pulse for 0. So here you can observe that at every decision instant, the desired pulse is having peak and other neighboring pulses are having 0 values. So the interference of other pulses in their bit duration, but no interfere at the decision instant. Thus the Nyquist pulse not only removes ISI but also results in the minimum bandwidth requirement for the same information. Nothing is perfect in this world, so now we will try to understand problems which are associated with the sinc pulse. So the first problem associated with the sinc function, that it extends from -infinity to +infinity, and it is non-realizable in the laboratory. If we truncate or limit it, then it will not be band limited in the frequency domain, and thus required bandwidth will increase and hence ISI will come back. Second point, it is very much necessary in distal communication that the receiver should be well synchronized in time. It means timing synchronization is very important in case of distal communication. And and receiver is also aware of the start time and the end time of the pulse. If there is a small timing error in synchronization, then significant interference of the neighboring pulses also occur, and ISI returns back, and hence probability of error increases. So you can see here that various pulses are transmitted. Again, we are taking the same example that we have transmitted 10111, and we have some decision instant at t is equal to 0, t is equal to tb, twice tb, and so on. But if suppose there is some timing error, then certainly this decision instant will shift, and suppose that is denoted by the red dots. And if you see that if decision instant is slightly shifted, then at the decision instant also we are getting the interference from other pulses. So now our concern here is to reduce or remove the ISI even if there is a small timing synchronization error. We have seen that ISI is present due to side lobes of the sinc pulse. It means since we have the timing synchronization error, and because of that other side lobes of the other pulses are basically interfering with in the decision instant. So if we can reduce the amplitude of the side lobes and make the main lobe narrower, then interference of the other pulses at the decision instant can be reduced, and hence ISI can be suppressed significantly. Nyquist suggested the solution in the form of raised cosine pulses. So in raised cosine pulses, we have narrower main lobe and reduced side lobes. So equation of this raised cosine pulse in time domain is Pt is equal to sinc RBT. So again you can see that same sinc function is there, but additionally it is having the product with the function cos pi alpha RBT upon 1 minus 4 alpha square RB square and T square. Here additional term you are seeing, that is alpha. So this alpha is termed as a roll-off factor. From the time domain representation of the raised cosine pulse, as the value of the alpha is increasing, the main lobe becomes steeper, narrower, while the side lobes are reduced as compared to sinc pulse. So you can see if alpha is equal to 0, then it is nothing but the sinc pulse, and if you are increasing the value of the alpha, certainly the main lobe is becoming narrower and side lobes are reducing. In frequency domain representation of the raised cosine pulse, we can observe that the bandwidth of the raised cosine spectrum is Rb by 2 for alpha is equal to 0, but Rb for alpha is equal to 1. For alpha is equal to 0.5, it is somewhere in the mid. So as you are increasing the value of the alpha, certainly the bandwidth requirement is also increasing. So since cosine term is multiplied here with the sinc pulse, that's why this is termed as a raised cosine pulse. Where alpha is equal to 0, when alpha is equal to 0, cosine terms becomes 0, and it is nothing but the sinc pulse. Hence we can say that sinc pulse is a special case of raised cosine pulse. We already know that how cosine signal look like. Now, since value of the cosine signal is always less than 1, and when points on the sinc curve are multiplied with this cosine function, amplitude of the points decreases. As we increase the value of the alpha, overall product at every instant of time or at every instant the amplitude reduces, and because of this the main lobe becomes narrower. Now if we observe the denominator, as the time increases, the denominator part also increases significantly and hence reduces the side lobes. So side lobes get reduced due to cosine term and also because of the denominator. But we also have to notice that as we are increasing the value of alpha, the bandwidth requirement is also increasing. So in this case, you can find out that the excess bandwidth is alpha times Rb by 2. If alpha is equal to 0, so excess bandwidth is 0, and if alpha is equal to 1, this is Rb by 2. And we already know that value of the roll-off factor alpha lies between 0 and 1 only. Then total bandwidth of the raised cosine spectrum will be Rb by 2 into 1 plus alpha. If in a problem it is given that 25% excess bandwidth is required to suppress the timing synchronization error, then it means that the value of alpha is given to you, and that is 0.25. From here, it is clear that more the timing synchronization error, more the value of alpha you require. But at the same time, more will be the bandwidth requirement. So more the error, more the value of alpha, but more the bandwidth requirement. Now, depending upon the extent of the timing synchronization error, we need to narrow the main lobe and reduce the side lobes. If timing error is not present, then we should not transmit raised cosine pulse. Even sinc pulse is sufficient, or you can say alpha is equal to 0 we have to take. If timing error is there, then we need to carefully choose the value of the alpha. It should not be very large because bandwidth requirement is going to increase then, such that we can minimize the ISI with minimum access bandwidth, but in the case ISI is not completely absent, it is only reduced. Also, we can observe from the formula of sinc function and a raised cosine function that in case of sinc function, it decreases with the rate of 1 by t. But in the case of raised cosine function, it decreases with the rate of 1 by t cube. So as the value of alpha increases, fall time sharply decreases. Thus the raised cosine spectrum becomes significant for pulse shaping. Stay healthy and safe. Thank you.